Black powder was the original game changer. It's the explosive that helped shape the modern world, even though by today's standards it's barely considered an explosive at all. Made from a simple mixture of saltpeter, charcoal, and sulfur, it was accidentally discovered by Chinese alchemists in the 9th century while searching for an elixir of immortality. Instead of eternal life, they ended up creating gunpowder. The biggest thing to understand is that black powder doesn't actually detonate. It deflagrates, meaning it burns incredibly fast instead of producing the powerful shockwave associated with modern high explosives. That's why it can propel a bullet out of a firearm or send a firework soaring into the sky without instantly shattering the object that contains it. Using TNT as the standard reference at 1.0 on the relative effectiveness scale, black powder comes in at roughly 0.55. By modern standards, that's fairly weak. It's also incredibly dirty, producing thick clouds of smoke and leaving behind heavy residue that quickly fouls firearms. Those drawbacks are exactly why smokeless powder eventually replaced it. Even so, for nearly 1,000 years, black powder was the most powerful substance humanity had ever put to practical use. Then there's TNT, the benchmark by which virtually every other explosive is measured. Whenever you hear someone describe an explosion as being equivalent to a certain number of tons of TNT, it's because TNT serves as the universal baseline with a relative effectiveness value of exactly 1.0. What surprises a lot of people is that TNT isn't the most powerful explosive ever created. It's simply the standard everyone compares against. It was first synthesized in 1863 by German chemist Julius Wilbrand, who originally developed it as a yellow dye. For decades, no one considered it especially useful as an explosive because it was so difficult to set off. Ironically, that became its greatest advantage. Militaries quickly realized that TNT was exceptionally stable. It could be melted down, poured into artillery shells, transported over rough terrain, dropped, or even exposed to fire without detonating. It requires a dedicated blasting cap to trigger its full explosive reaction. Detonating at roughly 6,900 meters per second, TNT became the dependable workhorse of military explosives because it combined reliability, safety, and predictable performance better than almost anything else available. Before dynamite changed everything, the explosive everyone wanted to use was nitroglycerin. The problem was that it was notoriously unstable, and people handling it were paying the price. In 1867, Alfred Nobel found the solution by absorbing liquid nitroglycerin into a porous stabilizing material, transforming it into something that could be transported, stored, and handled far more safely. That single breakthrough revolutionized mining, tunneling, and large-scale construction projects around the world. The fortune Nobel earned from that invention ultimately funded the Nobel Prizes that still bear his name today. On the relative effectiveness scale, dynamite rates around 1.25, making it stronger than TNT. But Hollywood has created some major misconceptions about how it behaves. A stick of dynamite doesn't explode just because someone shoots it or lights the fuse in dramatic fashion. Modern dynamite still requires a blasting cap to detonate properly. The real danger comes from old, deteriorated dynamite. As it ages, unstable nitroglycerin can seep to the surface, creating crystals and liquid deposits that become extremely sensitive to shock or friction. Fresh dynamite, when stored and handled correctly, is actually one of the safer high explosives ever developed. Next is C4, the military's go-to plastic explosive and probably one of the most misunderstood substances in action movies. C4 is primarily made from RDX mixed with a plastic binder that gives it a soft, moldable consistency. That flexibility is exactly what makes it so valuable, allowing it to be shaped precisely onto doors, bridges, steel beams, or virtually any target that needs to be demolished. With a relative effectiveness of about 1.34, C4 is also highly brisant, meaning it excels at shattering solid materials rather than simply pushing them apart. Here's the part that movies almost always get wrong. Shooting C4 won't make it explode. Setting it on fire won't either. Dropping it, striking it, or tossing it around isn't enough. In fact, soldiers have famously burned small pieces of C4 as an emergency heat source to warm field rations because it simply burns instead of detonating. The only reliable way to set it off is with a properly placed blasting cap that delivers the intense shockwave needed to initiate the explosive reaction. That exceptional stability is exactly why C4 has become the gold standard for military demolition. It's incredibly powerful when used as intended, yet remarkably resistant to accidental detonation. Semtex fills a similar role to C4, but its reputation comes from a far darker history. Developed in Czechoslovakia during the 1960s, it combines two powerful explosives, RDX and PETN, into a durable, moldable plastic explosive with a relative effectiveness ranging from about 1.25 to 1.35. For many years, Semtex had one characteristic that made it especially feared. It was extremely difficult to detect. It had very little odor and was challenging for early security screening systems to identify, making it a preferred choice for terrorist attacks. Its most infamous use was the 1988 Lockerbie bombing. That tragedy led to major international changes. Today, manufacturers are required to include chemical detection taggants and odor additives so the explosive can be identified more easily by modern security systems. So when you hear Semtex described as some uniquely devastating super explosive, that reputation is largely exaggerated. In terms of raw performance, it's comparable to other plastic explosives in the same class. Its notoriety came from how easy it once was to conceal and smuggle, not because it was dramatically more powerful than its competitors. Now you've heard RDX mentioned several times, in both C4 and Semtex, and that's no coincidence. RDX is the foundation that makes many of the world's most effective military explosives possible. RDX is the powerhouse hidden inside a huge percentage of the world's military explosives. In fact, the name is commonly said to stand for Research Department Explosive. On its own, it's an incredibly capable high explosive, scoring around 1% on the relative effectiveness scale and detonating at approximately 8,750 meters per second, significantly faster than TNT. Although chemists had known about RDX since the late 1800s, it wasn't produced on a massive scale until World War II, when militaries urgently needed something more powerful than TNT. So why isn't pure RDX used everywhere? The answer comes down to practicality. In its pure form, it's more sensitive than military planners would like for routine handling. To make it safer and more versatile, it's almost always blended with other materials or stabilized using waxes, oils, or plastic binders. Combine RDX with a plastic binder, and you get C4. Mix it with PETN, and you have Semtex. Blend it with TNT, and you create Composition B. Think of RDX as the engine powering many of the world's best-known military explosives. The rest is simply the packaging designed for a specific purpose. PETN is another remarkably powerful high explosive, actually edging out RDX with a relative effectiveness of roughly 1.66. It detonates at around 8,400 meters per second and plays a critical role in many explosive systems. You'll often find it inside detonating cord, where it carries the detonation from one charge to another, or inside blasting caps, where it serves as an extremely effective booster. But PETN has a fascinating dual identity. In tiny, carefully controlled medical doses, it's prescribed to help treat certain heart conditions by relaxing and widening blood vessels. The same basic physiological principle that makes nitroglycerin useful as a cardiovascular medication. It's remarkable that a compound from the same chemical family, capable of demolishing reinforced structures, can also help relieve chest pain. PETN does have one significant drawback. Compared with TNT or RDX, it's more sensitive and easier to initiate under the right conditions. Historically, it was also difficult for older security screening systems to detect. That combination is one reason it has repeatedly appeared in high-profile concealed explosive plots over the years. It's a compound that combines exceptional power, genuine medical value, and a level of sensitivity that demands careful handling. Now let's talk about the explosive that dominates the world by sheer volume. And it isn't some advanced military compound. It's ANFO, short for ammonium nitrate fuel oil. Made from ordinary ammonium nitrate fertilizer mixed with fuel oil, ANFO accounts for the overwhelming majority of explosives used in mining, quarrying, and large-scale excavation around the globe. Its popularity isn't because it's especially powerful. On the relative effectiveness scale, ANFO sits at only about 0.74, making it less powerful than TNT. But when you're moving mountains or blasting through solid rock, individual power matters far less than affordability, stability, and the ability to produce enormous quantities economically. One of ANFO's biggest advantages is also one of its most important safety features. It's so insensitive that it generally won't detonate reliably on its own. It requires a separate booster charge to initiate the full explosive reaction, making it considerably safer to transport and handle in industrial operations. Unfortunately, the widespread availability of its ingredients has also led to criminal misuse. The most infamous example was the 1995 Oklahoma City bombing, where materials intended for legitimate industrial purposes were turned into a devastating weapon. Few explosives have a reputation as intimidating as nitroglycerin. This is the liquid that changed the history of explosives forever, and for good reason. First discovered in 1847 by Italian chemist Ascanio Sobrero, nitroglycerin proved to be so dangerously unstable that Sobrero himself reportedly discouraged its widespread use. Pure nitroglycerin can react violently to shock, friction, or rough handling. That extraordinary sensitivity is exactly what made Alfred Nobel's invention of dynamite so revolutionary. By stabilizing nitroglycerin inside an absorbent material, he transformed an unpredictable liquid into something that could be transported and used much more safely. Nitroglycerin ranks around 1.5 on the effectiveness scale, making it unquestionably powerful. Yet it also presents one of chemistry's greatest contradictions. In extremely small doses, nitroglycerin has been used for generations as a medication to widen blood vessels and treat angina. Workers in early nitroglycerin factories often developed severe headaches caused by dilated blood vessels during the workweek, only to experience chest pain after spending weekends away from exposure, a phenomenon that eventually became known as Monday disease. It's one of the clearest examples of how the same chemical can be both extraordinarily dangerous and genuinely life-saving, depending entirely on how it's used. Finally, let's clear up one of the biggest misconceptions in movies and video games. Thermite is not an explosive. It doesn't detonate, it doesn't generate a powerful blast wave, and it isn't designed to demolish buildings. Thermite is an incendiary composition typically made from a metal powder such as aluminum combined with a metal oxide like iron oxide. Once ignited, it undergoes an extremely energetic chemical reaction that produces molten iron, and temperatures approaching 2,500 degrees Celsius. Its purpose isn't to explode, it's to burn with incredible intensity. That intense heat allows thermite to melt directly through steel, which is why it's legitimately used to weld railroad tracks and, in military applications, to permanently disable equipment, seal gun barrels, or destroy artillery pieces so they can't be captured and reused. Hollywood often portrays thermite as if it behaves like a bomb, but the reality is very different. Instead of a violent blast, it creates a blinding stream of molten metal that burns relentlessly downward. Because the reaction generates its own oxygen, simply covering it or pouring water on it won't stop it. It's not fast or explosive. It's slow, incredibly hot, and once the reaction begins, extremely difficult to interrupt. So that's 10 of the most well-known explosive and incendiary compounds covered. Which one surprised you the most? Did the medical use of explosives surprise you more, or the fact that thermite isn't actually an explosive at all? Let me know in the comments. I'm curious which fact caught you completely off guard. Next up is napalm, a weapon built around one simple idea: make fire stick. Like thermite, napalm isn't a detonating explosive. It's an incendiary weapon, and its effectiveness comes from chemistry rather than blast pressure. Ordinary gasoline burns quickly and splashes away from whatever it hits. Napalm changes that by adding thickening agents that turn the fuel into a sticky gel, allowing it to cling to surfaces while burning much longer and far more intensely. Developed at Harvard University in 1942, its name actually comes from the original chemical compounds used as the thickening agents. The concept was brutally straightforward. Fire that stays attached to a target causes dramatically more damage than fuel that simply flashes and burns away. Napalm burns at temperatures ranging from roughly 800 to 200 degrees Celsius, rapidly consumes oxygen in the surrounding area, and is extremely difficult to remove once it sticks. It saw extensive military use during World War II and later during the Vietnam War. Because of its devastating humanitarian impact, international law now places strict limits on its use against civilian populations. Its destructive power comes not from a massive explosion, but from relentless, persistent fire that continues burning long after impact. White phosphorus is another substance that's often misunderstood. Unlike most incendiaries, it doesn't need a spark or flame to get started. Simply exposing white phosphorus to oxygen in the air is enough to trigger ignition. It immediately bursts into intense flames while producing thick white smoke. For that reason, militaries have long used it to generate smoke screens, mark targets, and in some situations, for its incendiary properties. What makes white phosphorus especially feared is how difficult it is to extinguish. Cover the flames and remove oxygen, and the fire stops. But the moment fresh air reaches it again, it reignites. If it comes into contact with skin, it can cause severe chemical and thermal burns that are notoriously difficult to treat. U.S. service members commonly referred to it by the nickname Willie Pete. Like napalm, its use in populated areas is heavily restricted under international law because of the severe injuries it can inflict. It's a substance that needs nothing more than exposure to air to become dangerous, and one that repeatedly reignites whenever oxygen returns. Composition B represents a completely different philosophy. Instead of searching for one perfect explosive, engineers combined the strengths of several materials into a single formulation. Composition B blends RDX for its exceptional power, with TNT for its excellent casting properties, along with a small amount of wax to improve stability. The result delivers a relative effectiveness of roughly 1.33, making it more powerful than TNT while remaining practical to manufacture. This mixture solves a very real engineering challenge. Pure RDX offers tremendous performance but isn't easy to melt and cast into artillery shells or bombs. TNT, on the other hand, melts easily but doesn't pack the same punch. By combining the two, engineers created an explosive that could still be poured directly into munitions while delivering significantly greater performance. That balance made Composition B one of the most widely used military explosive fillers throughout much of the 20th century. There's no dramatic mystery behind it. It's simply smart engineering, the explosive equivalent of creating an alloy that combines the best qualities of multiple metals into one superior material. Before TNT became the military standard, another explosive dominated battlefields around the world: Picric acid. More powerful than TNT on paper, it was adopted by several major militaries in the late 19th and early 20th centuries under names such as lyddite and melanite. Compared to black powder-filled artillery shells, it represented a major leap forward in destructive capability. But chemistry eventually exposed a serious flaw. Picric acid reacts with the metal inside shell casings, gradually forming compounds known as metal picrites. Those compounds are dangerously sensitive and can detonate from surprisingly minor impacts or vibrations. In other words, ammunition could slowly become more hazardous simply by sitting in storage. Picric acid also left behind a stubborn yellow stain on nearly everything it touched. When TNT became available, offering nearly the same battlefield performance without the corrosion problems or growing sensitivity, militaries switched remarkably quickly. Picric acid wasn't replaced because it lacked power. It was replaced because its own chemistry slowly turned the ammunition containing it into a safety risk. Finally, we arrive at perhaps the most fascinating compound on the entire list: Octanitrocubane. Unlike the others, this explosive exists largely as a scientific achievement rather than a practical military material. Its molecular structure is built around cubane, an unusually strained cube-shaped arrangement of carbon atoms, with nitro groups attached in a way that packs an extraordinary amount of chemical energy into a remarkably compact molecule. On paper, the predictions are astonishing. Octanitrocubane is expected to outperform TNT, RDX, PETN, and nearly every other conventional non-nuclear explosive ever developed. But then theory and reality aren't always the same. The compound was first successfully synthesized around the year 2000, only after years of exceptionally difficult research. Producing even tiny laboratory samples requires an incredibly complex, time-consuming, and expensive process. Today, there is still no practical way to manufacture it on the scale required for military or industrial use. So octanitrocubane remains something unique, a milestone in chemistry that demonstrates what's theoretically possible rather than something you'll ever see deployed on a battlefield. Ironically, the most powerful conventional explosive on this list is also the one that's least likely to ever be used in the real world.